So, yeah, as the talk title says, we're going to talk about a little bit on Wi-Fi traffic modeling, and which I did at AT&T Research last summer as an intern. And the more recent work that I'm doing at Princeton, we have a short demo for transmitting video over wireless networks. So I'll try to keep 75%, 25% of the time that I have. So getting into the first part, as a brief outline, I'll give an overview of the data that we had from AT&T last year, which are Wi-Fi data sets that were collected from different hotspots, in particular from two different cities, San Francisco and New York. And based on that data, we did some kind of modeling and characterization, giving a framework as to how you would generate probably synthetic traces if you want to design and deploy a new protocol in the context of Wi-Fi hotspots. So there's three particular modeling that I'm going to talk about. The arrival count modeling, which will give a model for the number of customers that arrive at a given hotspot. The second one is the connection duration modeling, which is how long do they stay in a particular hotspot once they make an authentication connection to the access point. And the third one is the most important, that well, in terms of network capacity planning, you would want to know at any given point in time how many users are there. So that's the simultaneous number of users that are accessing a particular access point, and we want to model that distribution in a way so it would help us plan the capacity of the network that we will sustain. So I'll give so this was news from last year, June, where AT&T said that we want to increase the sales across Starbucks, McDonald's, hotels, and different other hotspots. So it says, in an effort to increase the sales and bringing more customers, Starbucks will now be offering Wi-Fi service free as of July. And this map I got from the AT&T website, where it says that in New York there are a total 1,416 access points. And in California there are about 4,000 access points. So AT&T has deployed these huge number of access points, and they have collected on and off data from all these hotspots. And the different colors here are for different types of venues. You can see a lot of yellows, which correspond to the McDonald's. We also have a lot of Starbucks, the green spots, which you cannot see so clearly. And the point is that the huge amount of Wi-Fi access point spread across the nation, and there's a lot of data. So how can we use it to do some good? Slide shows a brief system architecture as to how they collect the data. So on the premise, you have customers connecting with a smartphone or a laptop to an access point, and these are set up by AT&T. So in the network management device, they route you to the internet, and you want to tap it over here so that you know the session level data for each of the users. Let me give you a brief overview of the data that we had. So this was collected in March last year from New York and San Francisco. The venues were different coffee shops, fast food chains, bookstores, as in Barnes & Noble, and hotels, and so on. The different attributes of the data were the different connection login and logout times, how much bytes that were uploaded by each of these customers, and we also had characterization of the venue, as in where it is small or large or medium, the zip codes, and so on. There's a brief statistics. We had about 230,000 customers which logged in many times during this period of 1 month. So that's the number of connections. It's 1.3 million connections across 230,000 customers. If you know the zip code, there are 87 zip codes, and it's a duration of 4 weeks, a month's data.
What do you mean by number of devices? 10.
Number of devices are those big. I think these are the routers.
Oh, okay.
Yeah.
Not end user devices.
Of course.
That was confusing. Okay.
Yeah. So I'll show you some. So this I talked about a little bit earlier, that what we want to do with all this data, modeling different things in the network that will help us do a network capacity planning. So this graph shows typical arrival trend over 2 weekdays, and these are binned in 15-minute intervals. So the different colors are for different sizes of these coffee shops, tiny, small, medium, large, that we clustered based on the average number of arrivals for 15-minute bins. And the things to notice is that there are these 3 characteristic peaks that occur within a day. And if you notice the time, it's about 9:30, 12:31, and 6 or 6:30 in the evening. So it seems like at those times, there are a lot of people that are using or going to these coffee shops using a lot of wireless connections. And if you think about it, that maybe people go a lot to the Starbucks in the morning before going to work. That's typically the 9:30 a.m. peak we have. The next one is probably during lunchtime. And this one is probably after office work hours, that we have a lot of people coming into these coffee shops and using the facilities. Now, yeah.
Question. Regarding login logouts, do you have the MAC addresses of the devices?
Yes, these are mostly, well, they're not cell phones, these are cell phones as well as laptops. So for the cell phones, you have the IMEI and the phone number, so you can actually track down, but of course, that's a lot of privacy issues. We don't present any of those yet.
How did you get that when you're looking at them through Wi-Fi?
You mean the phone numbers and the IMEI? Well, they don't do deep packet inspection, I don't know for sure. At least in this one, they didn't do it. But I think when you connect with an AT&T Wi-Fi, you have to do some sort of login to your laptop if you're sitting in a Starbucks and connecting to AT&T Wi-Fi. So from that, we get that kind of data.
So it's in some database that you get to look at some log of records.
Right. I mean, the files that I looked at, every row contained a phone number, an IMEI number, and then the rest of the stuff that I told. Yeah. And there were about this 1.5 million records.
So you could actually maybe track the mobility across these 10 different devices.
You could, and that's what I was mentioning to him, that tracking the phone number or IMEI to the access points that this particular user is connecting, you could draw mobility patterns, that how it's moving. Yeah. It's very interesting things to do. So this graph I want to show that the difference between a weekday pattern and a weekend pattern. Now the blue curve is again a weekday pattern for, well, this case is for bookstores. There are 20 Barnes & Noble bookstores, and we averaged it out. Now see, for the weekend pattern, we don't see that 3 peaks anymore. We just have 1 peak, which is towards late afternoon. So probably kind of tells you expected behavior of a user, that on weekends, maybe it's too laid back, he goes to the coffee shop or bookstore towards early evening, late afternoon, and enjoys. So what this says that if we make a model for the arrival counts, we have to differentiate between a weekday model and a weekend model. In addition, these are aggregate statistics in terms of the total number of bookstores and the total number of coffee shops that I said. Now, if you plot for one individual coffee shops, that will be not so smooth, that will have a lot of ups and downs. But for individual venues also, we see these peaks. So the peaks kind of carry forward to if we're modeling the average arrival trends. But some customization needs to be done for venue-specific model. So this slide shows the bytes that were downloaded for 2 different kinds of venues, coffee shops and enterprises. And so this was plotted in the log scale density plot. coffee shops, as you would expect, that people stay there for a shorter time than in enterprises. Enterprise includes hotels and stadium where people stay overnight. Not in stadiums, but in hotels, or in bookstores, people stay longer. So coffee shops, we found a few KBs of data, whereas in enterprises, it varied a lot from a few MB to a few gigabytes. So we kind of went ahead and asked, what is the users doing downloading few gigabytes of data? And they said that these are computers that are the hotel computers that are connected to the Wi-Fi, overnight and for a long time. So in our modeling, we kind of discard this very tail where we had a few percentage of data that are in the GPs. And the thing to note is that in both these plots, we have a long tails. These are two plots that show the connection durations for each of these sessions. The left one is a cumulative distribution plot, and the right one is a complementary distribution plot. And this is a log scale. So you can see that the tail is very heavy for looking at the CCDF plot here. And also we have, this is 10⁻⁴, so this is like 20 minutes. We also see a lot of customers that spend less than 20 minutes to 15 minutes in each coffee shops. So it's not only the head that is long, there's also a significant amount of, there's not only a long tail, but there is also a significant amount of head in the distribution. So if you want to model this, you need a distribution that fits the entire range from the head to the tail. And this is a little statistics of how the durations, some mean and standard deviations across these venues. So I'll now jump into the modeling part of it. So first, the arrival count modeling. So we see that the data had a lot of time-dependent arrival rates. And we tried different, a few rather, modeling framework that we could use. One was the MMPP, the Markov modulated Poisson process. So there was a little difficulty modeling this whole arrival trend with MMPP because just of the deterministic characteristics of the peaks that occur at given 6:30, 12:30, and 9 and 6 p.m. in the evening. We tried with polynomial curve fitting to model it, but we could not fit the distribution with a small number of terms. So then we thought, okay, this is a time-dependent arrival process, and our final goal is to model the simultaneous number of customers that are present in each venue. So we would also want some further analysis on the model that we built for this arrival count. And we chose the non-homogeneous Poisson process, Poisson regression modeling with clustering to model the arrival counts.
So your time dependence you're talking about is in terms of hours of the day. There's certain busy hours. Is that what you're not thinking about like, within the 9 a.m. busy
No,
hour?
it's the entire.
It's over.
It's over the entire day, and because the day pattern repeats, if you model for a typical weekday, that would be good for each.
So if you said, let's always look at the kind of the 9 a.m. traffic per hour basis. You say, there's from day to, within the hour, do you see time dependence in arrival rates?
We do, yes. So in the modeling, that I'm going to show you, I break the hour into several bins, and then I cluster each bins depending on where the peaks are. Yeah. Okay, so here is what I was talking about. So let's say you consider a 1-day interval, and you break that 1 day into 15-minute slots. So 24 hours into 4, there are 96 such slots, right? And we looked at the data for each of these 15-minute slots, and we tried to cluster that at what time slots these arrivals tend to be approximately equal to each other. We used a typical k-means clustering techniques, and we found that there are 8 clusters that came out of these clustering techniques. And the nice thing to notice is that if you notice these green boxes, so the first one is between time slots 1 and 28, which is the first 28 slots. So each slot is 15 minutes, and this is so 1 hour is 4 slots, 28 would be 7 hours. And this is towards the end of the day, where it's just like 12 a.m. at night. So a day starts from 12 a.m. at midnight to the next 12 a.m. on the following day. So the clustering shows that these kind of wrap around. Now, if we look at the plots that I showed you for arrival counts, so this is starting from 12 a.m. midnight to around like 6 a.m., the first 6-7 hours. And this is the plot we have, this is the values from 12 a.m. So if you cluster it, you want these to be clustered with these. And that's what is shown in the cluster, that 1 to 28 is clustered with 94, 95, 96, which are these. We also want to have these belong to the same clusters because they are the peaks at almost equal values. So we have these values here. The slots number 35, 37, which correspond to about 12 in the noon, and this one is in the evening. So this clustering kind of gives us a nice way to combine the slots that have the similar number of arrivals within a day. And with that, we went ahead and we said, okay, let's break down a day into 8 bins, because we saw there are 8 clusters. So assume this is a day. We have 8 bins, so each bin is 3 hours. And each of these bins are now divided into, well, again, we have the 15-minute slot, but then within 3 hours we would have 12 slots. So if I am denoting the bins and J by denoting the time slots, so when I'm doing a Poisson regression modeling, these will serve as my auxiliary variables. Which is shown in this equation. So what I have, the lambda is the time-dependent average arrival count. Ij is kind of time, so you can think of this as t. Which is, if you take the log of that, the GLM, the Generalized Linear Model framework, says that it's a linear function of the coefficients, which are beta k, gamma k, delta, and alpha. And we used a third-order polynomial to have a satisfactory fitting in this case. So, so the first term alpha shows over a day mean arrival counts. The sum of the terms, the sum of alpha, beta k, and gamma k shows the differential effects across different clusters and slots within it. And the last term, delta of I star j, where I'm multiplying the bin number times the slot number, it tells you that it's a differential effect of slot j with respect to the particular bin. And what it's saying physically is that the arrival count that's occurring on slot 10 and bin 5 does not have to be the same. Does not have to be the same for slot 10 in bin 3. So we multiply their slot and bin numbers to get that effect. And there is one result I'm showing for the model that we got out of this framework. The blue line is the actual observed mean arrival rate for I think this is for coffee shops, right? So we have these 4 weeks of data. The first 3 weeks we used it for training the data set, and the last week used for testing and validation. And those are the number of arrivals that we worked with. So the blue plot is, first I average across all those arrivals, and then I average over all the weekdays. And this is a typical weekday plot for. So as we can see, our red curve captures the 3 peaks very nicely. And this is a plot to show that how does it fit with a path, in the sense that if you take 5 typical days, not average over, but 5 actual arrival rates, how does your model fit? So we have 4 different colors here. The cyan color, the light blue, is the actual data. And we see, of course, there is a lot of ups and downs in the data set. The red curve is what we got, the same, the model plot from the previous graph. And the blue and the green ones are the quantile, are the 5% quantile plots. So this is 97.5 and this is 2.5 quantile. And we see that I do not have the figures as to how many numbers go beyond these quantile range, but that's in the paper. And we saw that there was very good match with respect to how you model and how your path, actual path follows across 5 days. So because there were like 240 coffee shops, you cannot model each one of the coffee shops individually. So we do an aggregate model, and then we show that, okay, this lies within your statistical quantile range, and that's within 5% is good. So with the arrival count modeling, now we come into the modeling of the session durations. As I showed this plot before, the CCDF plot on a log-log scale, that it has a long tail, it also has a very significant amount of head in the distribution. So a few seconds to several hours with a very long tail. So as I said before, we need a distribution that not only fits the head, but also fits the tail of the distribution. And we use a distribution called the phase type distribution for modeling the duration, which says that if you take the logarithm of y, which is the duration, that is a linear function of the phase type random variable x. So y would be distributed as e raised to x. A few nice properties of phase type random variables. It's a sum of random number of exponentials. So you can imagine, well, so let me give a justification as to why we are doing a Poisson distribution, a non-homogeneous Poisson process modeling. You could imagine that there are lots of customers that visit these coffee shops, maybe in the order of thousands that visit these coffee shops. But someone actually using the Wi-Fi facility in the Starbucks is pretty small. So maybe 50 out of 1,000 use the Wi-Fi facility in the coffee shop. So the number n is very large, whereas the probability of using an access point is pretty small. And that kind of fits well into the Poisson framework. So another nice property of phase type is that this is dense in the class of all distributions, meaning that it not only captures the heads, but also captures the tail, which are a little different from what Pareto and Whipple can do. These would typically capture the tails very nicely, but not as much as the head for the entire range. And just to mention, the phase type random variables were first introduced by Marcel Nuyts in Purdue, and with whom my mentor was a student of his, so he was very interested in applying these phase type random variables to these kinds of scenarios. And we went ahead with it. So this is a plot once we had the phase type random variable with an order of 5 to fit the durations. So that's a CDF plot, and we see it matches pretty well with the actual observed data. And I said before, we had truncated some of the data that were connected for a long time, and we found that these laptops were actually owned by the hotels or the bookstores, and they are connected overnight. So that's not a customer pattern that we want to capture, so we have to truncate that data sets, which are beyond 6 hours and more. So what have we done so far? We have shown a model for the arrival counts, which was a time-dependent Poisson process. We showed a distribution fit to the connection durations using a phase type random variable. Now combining these two, we want to have a model for the number of simultaneous connections within a coffee shop, because at the end, that's what is very important for capacity planning. Is at any given instant, you want to know how many customers are connected to the y-axis point, so you could provision for that max load in every hotspot. So we show that the number of simultaneous connections could be equal to the number of busy servers in an empty G infinity queue, where the time-dependent Markovian arrival rates with generalized waiting time G, and infinity is the number of coffee shops servers. So the theorem says that the number of busy servers, Qt, which is the number of simultaneous connections, at any given time t follows a Poisson distribution with mean this quantity. So if you want to write the Poisson distribution, that would be e raised to this quantity, and then this quantity raised to n over factorial n, if you want to find the number of customers for any given n. So how do you prove that expression? Like, show the theorem, but how do you prove it? I'll show you a brief overview of the proof that we think were novel and not done in the literature before. So this proof is based on a semi-regenerative argument for MTG queuing system, MTG infinity queuing system. Couple of points that were interesting was that it does not require the system to be empty at some infinite past. So this fits well because from the arrival plots that we saw, we see that the system is almost empty after 12 a.m. in the midnight. So you don't have to go to some infinite past to apply this model. You go at the beginning of the day, the midnight, and your queue is empty. And there are some other assumptions which do not assume that are in the traditional proofs that are for MTG infinity queues. So one of the ways we found cool was to show that the probability generating function is given by this. So probability generating function is nothing but the power series for the PMF of the distribution, and for a Poisson process, it's given by e power z minus 1 times the lambda. So this is the lambda or m of t that I'm calling here. So you show that the PGF is equal to this, and then it would follow that the mean is just the quantity in the exponent of the e. And so we want to find out at time t how many customers are there in the system connected to the y-axis. So the idea we had was we kind of embed this smaller problem into a more general framework as to find the number of customers that arrived between time u and are still in the system at time t. So if you put u equal to 0, you have what you want, that the number of customers since the beginning that are still at time t. So consider the interval, and there could be two cases. One is that there is no arrivals that occurs between u and t. In that case, there is one term. The other term is that, let's say there is one arrival that occurs at time v. Now the arrival that occurs at time v could be in the system until t, or it could leave before t. And if it leaves before t, then we are back in the same situation that the system is empty. And that's the kind of semi-regenerative argument that we employ here. So these are the two cases, and the expression for the integral equations that we have. This is the term when there are no arrivals from u to t. And this is the term that, well, there are two terms. One is when the arrival is still in the system, and when is the arrival has, well, this is, I think, for the arrival is not in the system anymore, and this is when it's still in the system. So once you solve this integral equation with taking partial derivatives on both sides, you could derive the expression. You could solve for gt of zu, zv, which was, and you substitute e equal to 0, so you get this expression here. And that's how we show that uh, that the mean of the distribution is that. So after doing all this modeling, what we get? So here's a plot of these simultaneous number of connections plotted against the actual data, not averaged, but as before, the sine curve shows the actual number of customers that are at any given point. And these are again 15-minute pins across the time axis. And as before, we again do the quantile plots for 97.5 and 2.5 percentile, and we show that it falls within the statistical. So I think here, it's right here, so I don't have the data here. So this is useful for doing a capacity planning in the network. So I think this concludes the first part of the talk, and then I want to show a demo, but I have a couple of slides so that it gives enough background to what the demo that I'm showing. And this is the work I'm doing with a first-year grad student and Meng Chen at Princeton. So let me motivate this by two numbers. So we have 30 and 10. 30 is the number of percentage of downstream traffic from only Netflix, which was during the peak hours in the US. And 10 is the dollars charged once you exceed your 2 gigabyte quota by AT&T and Verizon. So the graph we see here is that video traffic is increasing at an alarming rate. That more and more users are using video traffic on their mobile devices, laptops, and so on. And this trend is conflicting. On one hand, we have a lot of usage, and on the other hand, we have these ISPs that are capping our unlimited plans and charging more money. So the question is there a way to have the consumer watch whatever number of videos he wants to watch, but stay within her monthly quota, and without suffering a noticeable distortion in the video that he's watching? So there's a trade-off along these three axes. Cost axis, which is related to the monthly quota. Let's say you have a $30 or $20 quota from AT&T, a data plan. The distortion is per video, which is measured. There are different metrics for measuring distortion, and PSNR, or the peak signal to noise ratio, is one of them. And of course, the number of videos. So we see if you we want to be at a place where you have low cost, of course, low distortion, and you want to watch a lot of videos. So the project is, or the system is called QAVA, QAVA standing for Quota Aware Video Adaptation. This falls under the broad theme of network-aware content generation. So you want to generate content that is conducive to the network. In this case, the network is kind of quota. You want to generate the video that is conducive to the quota that you have left in your monthly budget. So this figure shows a high-level system architecture of the prototype that we have made. So you have to use a device. It's one module, and you have two other modules, that is a stream selection module and a video profiler module. So what do you do? For every video that the consumer is requesting to watch, you have your video profiler to have it encoded at different bit rates. So let's say a video is 5 Mbps HD video, and by some profiler you have encoded it into, let's say, 10 different bit rates, starting from 1 MB, 500 KB, and as you go on. So the idea is that depending on how much quota is left to the user, you would want to select a video which has the least distortion, and also so that's what you want to do. You want to choose the bitrate of the video that has a much less distortion, while still trying to be within his budget. So let me show the video, and then I'll draw the conclusions. Okay. Is there audio going on this?
not through that cable. There's another cable we can plug in. Probably best to
Okay. I'll just explain. Yeah. Okay. Hit on that volume. So let me just show what these are. So these are two talk shows. The left one is the video that is being watched when there was no QAVA playing a role here. And this right plot is a video that is being played when there is QAVA, which means the bitrate selected by this one is different from the one that is selected by a non-QAVA system. And this video is being played by a user which was at the beginning of a billing cycle, so in the beginning of a month. Now you could imagine that a QAVA system which is in the beginning of the month would try to give not so low bitrate, but because it has the whole month left and it has the entire quota left, it will try to give a higher bitrate so that your distortion is not too much. So you can see that the wait.
On this screen, we see two sample videos that were watched at the beginning of the billing cycle. The non-QAVA system is very aggressive by choosing a high bitrate to provide the user with the best video quality, regardless of her quota or usage pattern. A QAVA user, on the other hand, continuously tracks the usage pattern and selects a stream appropriate to her quota, and therefore, although it chooses a lower bitrate than the non-QAVA user, we do not observe much distortion. On the second screen, we see two sample videos.
So just pause for a second. So we could not see any difference between the quality of the videos that were being played on two screens. That's because the non-QAVA system, which is on the left, is choosing a high enough bitrate in the beginning of the billing cycle, and there is not much distortion. Now this particular video, which is a Harry Potter video, is being watched towards the end of the month, when there is not much quota left to the user. So a non-QAVA system, our heuristic for the non-QAVA system is that whenever you exceed 80% of your quota, you kind of fall back to a lower bit stream. Whereas the QAVA user kind of tracks the user profile throughout the month, and it streams a much better quality video towards the end of the month, even when staying within the quota. So you can see a clear difference between the quality of the
that were
videos.
watched towards the end of the billing cycle. As expected, we observe a very high distortion for a non-QAVA user, to the point that the video is almost not watchable at all, compared to the QAVA-enabled user, who can still enjoy reasonably good quality video even when she is at the end of her billing cycle. We thus see that a QAVA-enabled user can stay within her monthly quota and enjoy good video quality by letting the system choose the right bit rates, through online programming of the usage pattern, and by exploiting video compressibility. The non-QAVA user, although she can watch high-quality videos at the beginning of her billing cycle, suffers toward the end of the cycle by either exceeding her quota and spending more money, or by being forced to watch poor quality videos.
So this is Harry Potter, and
Hey,
now,
so which was the bad one?
so the left one was the non-QAVA user. That was the bad one.
Maybe it's our projector, kind of.
Yeah, I know. As I was watching, it's much better on the screen.
So is this completely automatic, or does the user can the user say, well, this is just some video that I don't care so much about, but if I want to choose a low one for this one, so then I can add to my future quota.
Right. So we're going to have this system also interactive with the user. User say, okay, I don't care about this video. Like my teammate whose voice you just heard, Jessie. She says fashion shows are very important to her, whereas sports is completely crap. So. Yeah, so the user should have the option to select which ones he wants to watch at a much higher bitrate and which one not.
The other thing, I mean, I don't know if it's possible, but a lot of the shows now that you stream, they have commercials that you just can't get rid of. So I wonder if you can like drop the rate maximally on the commercial section and then not on the other section.
I think that's also possible.
Detecting when the actual.
Right.
I don't know if it's a good idea or not, but
No, have the commercial company pay you to watch it in high resolution.
Yeah.
that's interesting.
Add to your quota.
There are a lot of streaming software that you can't, like the Comcast on-demand thing. They won't let you go past the commercial.
Right.
They they would actually give you the opposite. They'd be like, we'll give you the commercial in very high quality. The rest.
Yeah. So for a clip that is short enough, like 2 minutes, you would not want to switch the bit rates. But for a long enough video, which is maybe more than 10 minutes, even you would want to switch the bit rates even within the video.
But shouldn't the policy at the beginning of the month really depend on the a priori knowledge of,
Yes, of course.
of the usage statistics?
Yes, so that's what is our user profiler does. It kind of tracks that usage pattern and tries to build a profile for every user. And so far we haven't done that extensive experiments, but we have an online machine learning algorithm that would track the user, and maybe we find that some user is a lot more watching a lot more videos during weekends or during late evening nights. So
Does that matter?
Hmm?
Does that matter?
That would matter because if you know that, let's say you are towards the end of a month and the month ends with a weekend, and you know that the user is going to watch a lot of videos during that time, and maybe the videos that he's watching in the week, you would want to kind of provision a lower bitrate so that he could watch movies and stuff like that, which matter to him a lot towards the end of the month. So having this profile is very useful.
So roughly, these streams that you're getting, like a half an hour of either a movie or a TV show or whatever, how many gigabytes is that onto a phone? Because I know I know a movie is 5 or 6 gigabytes in DVD quality, on a big screen, but
on the iPhone, the resolution, if you are, I think the iPhone 4s only record at HD, that is 720p. It's 1280 by 1080. That's how it records it. But the screen is much smaller. The screen is even the iPhone 3 are 640 by 480 resolution screen sizes. So we saw that with that resolution, a video that is let's say a minute video, which you could watch pretty clearly, could be just a couple of MBs, not more than that.
So you can watch like 100 videos, 100 minutes per month. So is it like if it's 2 megabytes, then a gigabyte is 50 of those minutes?
So you have
2 megabytes, 50 of those is 100 megabytes. So you get like 5,000 minutes of
1,000
video.
minutes, probably. Yeah. 1,000 minutes of good video, and that's watching 8 movies. Yeah, that's 8 movies.
So is this work sponsored by AT&T?
No, this one is not from AT&T. This one is
Way
from
below
Princeton.
the American.
Okay, the previous
The
work
previous was from
was from
That's like
AT&T.
30
Do you
minutes.
have the numbers of how much bandwidth their hotspot, like backhaul, they have? Usually,
Somebody wants
and
the phone.
their backbone capacity that's coming out of the T1 lines.
it's T1 line?
It's T1 lines, yeah.
So all the Starbucks is which is
They have
T1 line?
T1 lines, yeah.
Okay. And they're not like the big store and small store.
I don't know about that details, but I think typically from the Starbucks they have that T1 lines coming. Maybe from hotels they might have something else. I'm not sure. So let's just complete this plot.
This first graph shows the cumulative consumption of usage over time, measured in megabytes, for a user from Bob's label.
Okay, I think this is this audio. So let me explain what is it. This is tracking these are the 20 videos that are watched, and we actually ran this in the lab with some volunteers that they're watching the video on the system. And the left-hand side is the Quota. So the non-QAVA user, I think the quota in this case was about 140 megabytes per user. So it's kind of overshooting the quota at this point, whereas QAVA is trying to be within the quota until all the videos are being watched. So show that distortions that is called.
QAVA labeled user always do the minimum monthly quota by having the system choose the appropriate figures for growth throughout the term zone. The system accomplishes this by profiling and predicting the user behavior using time series prediction, online naming, and stream selection algorithms. The second graph shows the distortion of the videos chosen for non-QAVA and QAVA user. We observed that even though the Quota user was able to stay within her boundary budget on the previous graph, by choosing lower and more appropriate bit rates commensurate with her use.
So let me explain what's happening here. On the left-hand side, on this axis, we have the ratings for the videos. So we had 20 volunteers in the lab that watched all these videos, and they rated in the scale of 1 to 5. And that's usually called the MOS, or the mean opinion score. And it's a very subjective measure of the video quality. As opposed to PSNR that I talked about, which is an objective quality that you can calculate using a formula. So the thing to notice in this graph is that towards the beginning of the billing cycle, when the non-QAVA, the blue dots are choosing a very high bit rate. So you see the scores are very high. Whereas the QAVA user kind of oscillates, the red dots are everywhere. So it's choosing a little lower bit rate throughout the billing cycle, which would cause not so much distortion. And towards the end of the cycle, we see that the blue dots are towards the end here, whereas the red dots are at least giving you 3 to 5 rating for each of these videos. So it's kind of
on the whole, this seems to argue against your system rather than.
what is
You
it?
think it's a favorable result?
It's forced to watch the videos.
No, I'm just curious because there's as many blue dots, fewer blue dots which are dipping down than red dots. If you took the average
Well,
mean opinion score, it looks like pretty close with QAVA a little below.
no, the other thing to notice is that these blue plots, even though they're high, they are exceeding the quota.
Yeah, no, that I agree, but
So there are two
that
axes
make
here.
that extra. So somehow you've set your learning algorithm in a way that it's probably saving you money, but
Saving you money.
worse quality.
Not as much worse that you cannot watch, and that's the whole video profiler is
So
doing.
if you watch it, I mean, this way, at least 3 weeks in a month, I'm getting nice quality, and this one, it's all over the place. Like you have some mean opinion scores of
Right, it's
ones,
ones, a few of them
so
are
that was
few
the
ones.
sports that you wanted to watch. And so in some
No,
way,
I think if that would not be the sports. That would be the talk show probably. to check out.
but that comes back to this whole issue of can we build personal assistants which make good decisions on our behalf, and it's not really.
I think we need more data to run the system. This is over 2 days we watched these videos. We have a better profiling of the user behavior over a month or 2 months. And then we
But
had
I
only
think that one suggestion would be that if you use some cross-layer information from the network, you might be able to improve the scheduling and thereby improve your actual stream performance. So this one is kind of independent of what the network is doing,
right.
but you might be able to
Combined with some
do a
network
tighter
metric.
integration where you can get better quality with the same number of bits.
Okay. So let me just.
So this is better. This was using UDP-based players, or was it a TCP-based player?
This is actually using this. We did a little modification on the Microsoft Silverlight that Netflix is using.
I think that's it.
So that's HTTP. Yeah, HTTP
HTTP
TCP.
download.
Yes. Okay, so let me just draw the conclusions and then we'll take questions. So the first part, we showed a modeling framework for the Wi-Fi traffic in large-scale public hotspots. And we showed 3 different kinds of model for doing capacity planning of the network. One was arrival count modeling with the non-homogeneous Poisson process. The second one was phase type distribution to model the connection durations. And in the third one, we showed a modeling of using MTG infinity queues to get the simultaneous number of customers in the system. And the highlight was that we have a novel proof using the regenerative argument for the MTG infinity queue. And the second one was a practical end-to-end system for Quota video delivery. And that's it. Thank you very much.